There are just over 12,500 nuclear warheads on Earth right now, spread across 9 countries, sitting quietly in silos, submarines, and storage bunkers. It sounds like an almost unimaginable amount of destructive power. Enough, we're often told, to end civilization many times over. So here is a strange, almost childish question that turns out to have a genuinely fascinating answer. What would happen if you took every one of those warheads and every planet in the solar system and put them together? Could humanity's most fearsome invention actually destroy a planet? Could it destroy all of them? The answer, it turns out, is a resounding no. And understanding exactly why reveals something profound about the difference between how powerful something feels to us and how powerful something actually is on a cosmic scale. To even begin answering this, we have to start with the biggest, angriest thing humans have ever built and detonated, the Tsar Bomba. On October the 30th, 1961, the Soviet Union dropped a bomb over the Arctic island of Novaya Zemlya that remains, to this day, the most powerful explosion ever created by human hands. Its yield was somewhere around 50 megatons of TNT equivalent, more than 3,000 times more powerful than the bomb dropped on Hiroshima. The fireball was visible from 600 miles away. The mushroom cloud climbed roughly 40 miles into the sky, 7 times taller than Mount Everest, punching through the stratosphere itself. The shock wave was so immense that it circled the entire planet 3 times, and it was detected by seismographs on the opposite side of the globe. The bomber that dropped it was given only a 50% chance of escaping the blast, and it fell hundreds of meters in altitude from the force of the shock wave alone before limping back to safety. It was, by any human measure, an almost apocalyptic event. And yet, on the scale of a planet, it was nothing. Less than nothing. To understand just how small nothing really is here, we need to talk about something physicists call gravitational binding energy. And once you understand this one concept, the entire fantasy of nuking a planet apart collapses in the most satisfying, humbling way. Every planet, every moon, every star is held together by gravity. Trillions of tons of rock, metal, gas, and ice are all pulling on each other, all the time, crushing themselves into a ball. To actually destroy a planet, not just crack its crust or blow a crater in it, but to genuinely tear it apart and scatter its pieces into space so they never come back together, you would need to supply enough energy to overcome all of that mutual gravitational attraction at once. That total amount of energy is the gravitational binding energy, and it scales with a planet's mass and size in a way that is almost cruel to anyone hoping to fight it with explosives. For Earth, that number works out to something like 224 sextillion megajoules, or in more digestible terms, about 2.24 times 10 to the 32nd power of joules. The Tsar Bomba, our biggest bomb ever built, released around 2.1 times 10 to the 17th power of joules. Do the division, and you find that Earth's gravitational binding energy is roughly a quadrillion times greater than the energy of the most powerful weapon humanity has ever detonated. A quadrillion. That's a 1 followed by 15 zeros. If you wanted to physically shatter the Earth using Tsar Bomba-class weapons, detonated all at once, you would need something on the order of a quadrillion of them. A number so large it dwarfs not just our current stockpile, but every bomb humanity could plausibly build in the next 1,000 years, even if every nation on the planet devoted its entire industrial output to nothing else. And Earth, believe it or not, is one of the easier targets. And let's start smaller and work our way out, because the story changes dramatically depending on which world you choose to attack, and the differences are where this gets genuinely interesting. Take the moon first, since it's the smallest, closest body we might imagine nuking. Its gravitational binding energy is far lower than Earth's because it's much less massive and much less dense in terms of total gravitational self-attraction. Even so, cracking the moon apart would require something on the order of 600 billion Tsar Bomba scale detonations, all delivered simultaneously. To put that in perspective, that total energy release would be roughly equivalent to the entire output of the sun over about 6 minutes. 6 minutes of the sun's energy, compressed into a single moment, aimed at a lifeless ball of rock 250,000 miles away. And that's the smallest, easiest world in our neighborhood to break apart. It's worth pausing on that. The moon has already survived worse than we could throw at it. Its surface is a graveyard of ancient impact basins, including the South Pole Aitken Basin, one of the largest impact craters in the entire solar system, gouged out by an asteroid collision billions of years ago. That single ancient impact released energy on the order of 4 times 10 to the 26th joules, a staggering amount, and yet still roughly 300 times smaller than what would be needed to actually destroy the moon as a body. The moon didn't just survive that hit. It barely noticed it, cosmically speaking. Now let's move to Mars, because Mars carries an extra layer of cultural weight in this conversation. Not because anyone has seriously proposed destroying it, but because one very famous person has spent years floating the idea of nuking it for an entirely different reason. Not to blow it apart, but to warm it up. Elon Musk has talked publicly, on and off since 2015, about detonating nuclear weapons continuously above Mars's polar ice caps, essentially creating small, repeating flashes of heat, what he's described as two tiny pulsing suns, in order to vaporize the frozen carbon dioxide trapped there and thicken the planet's paper-thin atmosphere. The idea is that releasing enough carbon dioxide into the Martian sky could trigger a runaway greenhouse effect, trap more heat from the sun, and gradually warm the planet enough to allow liquid water to exist on the surface again, the way scientists believe it may have billions of years ago. It's a seductive idea, straight out of science fiction, and Musk has doubled down on it more than once, insisting that nuclear detonations would happen high above the surface and wouldn't leave the planet radioactive, more like a fusion flash than a fallout-producing blast. The problem is that the science doesn't cooperate. In 2018, a team of planetary scientists led by researchers including Bruce Jakosky published a study in the journal Nature Astronomy that tallied up all the accessible carbon dioxide on Mars in its polar caps, in its dust, absorbed into its rocks, and concluded that even if you released every last molecule of it, you still wouldn't have enough greenhouse gas to meaningfully thicken the atmosphere or warm the planet in any lasting way. Mars, it turns out, simply doesn't have the raw material. It's not a matter of needing a bigger bomb. It's a matter of the planet's own chemistry running out before the plan even gets started. Roscosmos, Russia's space agency, went further and put a number on it, estimating that terraforming Mars this way would require detonating something like 10,000 nuclear warheads, a suggestion Musk waved off almost casually on social media, saying it was no problem. Other scientists have pointed out an even stranger risk, that nuking the poles could backfire entirely, since the dust and particles thrown into the Martian sky might form clouds that reflect sunlight away from the planet, actually cooling it rather than warming it. So even in the one scenario where nuking a planet has a real, non-destructive purpose, warming Mars rather than shattering it, the honest scientific consensus is that it wouldn't work, at least not with anything resembling present-day or even near-future nuclear technology. If Mars resists our fantasies through simple lack of material, the giant planets resist through something far more overwhelming: sheer mass. Jupiter is the true monster of our solar system, more massive than every other planet combined, more than 300 times the mass of Earth. Its gravitational binding energy isn't just bigger than Earth's, it's staggeringly, almost comically bigger. Scientists estimate that destroying Jupiter would require energy equivalent to about 100 billion trillion nuclear bombs, a 1, followed by 23 zeros. To put that number into some kind of human perspective, if every single nuclear weapon on Earth today, all 12,500 of them, were somehow each as powerful as the Tsar Bomba and detonated together every second without pause, it would still take longer than the current age of the universe to accumulate enough energy to unbind Jupiter's mass from itself. Saturn, Uranus, and Neptune, while less massive than Jupiter, are still gas and ice giants dozens of times more massive than Earth, and each one would demand its own almost incomprehensible tally of bombs, numbers so large they stop meaning anything intuitive and simply become abstractions, digits on a page. These worlds didn't form gently. Jupiter and Saturn likely swept up. Material for millions of years, growing so massive that their own gravity began crushing hydrogen gas into strange, exotic states of matter deep in their interiors. Metallic hydrogen, thought to conduct electricity like a metal, despite being, on the surface, just an ordinary gas. A planet built from that much compressed, crushed material isn't something a chemical or even a nuclear explosion is ever going to trouble. So if planets are effectively immune to human weapons, why does gravitational binding energy scale this way? Why is Jupiter so disproportionately harder to destroy than Earth, which is itself disproportionately harder than the Moon? The answer lies in a beautifully simple piece of physics. Binding energy doesn't just depend on how much mass a body has, it depends roughly on the square of its mass divided by its radius. Add more material to a planet, and every new layer isn't just adding weight, it's adding gravitational pull that reaches back and squeezes everything already there even. Tighter, it's a compounding effect, a snowball that gets exponentially harder to unmake the bigger it grows. This is precisely why, if you wanted to talk about genuinely disassembling a planet-sized object with energy on a scale nature actually uses, you'd need to look not at nuclear weapons, but at cosmic scale events, the kind of thing that happens when a star's core collapses in a supernova, unleashing more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. Even then, that energy isn't purposefully aimed at destroying a planet. It simply happens to be so vast that anything nearby, including planets, gets swept up as an afterthought. This brings us to an obvious next question. Since we've talked about worlds that are too small or too massive, what about something in between, or something that isn't really held together by gravity in the same overwhelming way? Consider an asteroid. This is actually the one place where humanity's existing technology genuinely does matter, and where the physics tips, at least partially in our favor, because small asteroids aren't crushed together by gravity nearly as strongly as planets are. Their structural integrity often comes more from weak physical bonding, loosely packed rubble piles, held together by mutual friction and tiny gravitational tugs, rather than the overwhelming self-gravity of a planetary body. This is why, in 2022, NASA's DART mission was able to nudge the orbit of a small asteroid moonlet called Dimorphos, simply by slamming a spacecraft into it at high speed, no nuclear weapon required, and successfully altered its orbital period. It's a small, controlled demonstration, but it's proof that humanity has real, functioning tools for planetary defense against space rocks. Tools that work not by achieving some fantastical gravitational binding energy threshold, but by using precision and momentum instead of brute force. If a genuinely dangerous asteroid were ever found on a collision course with Earth, the plan wouldn't be to nuke it into 1,000 pieces, since that risks turning one large threat into many smaller radioactive ones on similar trajectories. The plan would be to nudge it, gently, years in advance, so a tiny change in its path compounds into a wide miss by the time it reaches Earth's orbit. Which brings us back, with a bit of humility, to the fantasy we started with, the idea of gathering up every nuclear weapon on the planet and using them to attack the solar system itself. Even if every nation cooperated, even if every warhead in every silo, submarine, and storage facility were detonated at once, the combined yield would amount to a few thousand megatons at most, an amount that, however horrifying for life on Earth, remains a rounding error against the gravitational binding energy of literally any planet in our solar system, including the smallest ones. Mercury, the smallest planet, still outweighs our entire nuclear arsenal's destructive potential by many orders of magnitude. Even Pluto, no longer officially classified as a planet, but still a substantial icy world hundreds of miles across, holds itself together with a gravitational grip that no stockpile of chemical or nuclear devices built by human hands could ever hope to overcome. The numbers simply don't work in our favor. They were never going to. And maybe that's the real hidden gift of this thought experiment. We build these weapons and we call them, with a kind of grim pride, world-ending. We test them in remote deserts and Arctic islands and watch mushroom clouds rise higher than any mountain on Earth. And it feels, in that moment, like we've touched something godlike, something capable of undoing creation itself. But step back, put that same explosion next to a planet, even the smallest, driest, most lifeless planet in our solar system, and the fantasy evaporates almost instantly. Our biggest bomb looks less like a hammer against a planet and more like a single spark thrown against a mountain, a flash of light and heat that vanishes into the vastness of what it was aimed at, changing nothing about the mountain's fundamental shape. Planets are not fragile. They are, each one of them, the product of billions of years of gravity slowly, patiently, relentlessly gathering matter into a single, overwhelming mass, layer upon layer, crushing itself into a stable, self-reinforcing whole. That's not a structure. A species that has only had nuclear weapons for 80 years is going to unravel with a few thousand bombs, no matter how apocalyptic those bombs feel to the civilizations living on the surface of one particular, comparatively fragile, blue world. There's something quietly reassuring in that, and something quietly humbling too. Reassuring because it means our worst weapons, as horrifying as their effects on human life and human cities would be, are not capable of literally erasing a planet from existence. The Earth itself, as a physical body orbiting the sun, would survive our worst mistakes intact. Its rocks and oceans and atmosphere still bound together by the same gravity that assembled it 4.6 billion years ago, ready, eventually, for whatever comes next. And humbling, because it puts our self-image as a technologically powerful species into sharp, sobering perspective. We can end civilizations. We are nowhere close to ending worlds. Out there, planets like Jupiter sit with a gravitational binding energy so enormous that the number of nuclear weapons required to unmake it doesn't even fit comfortably into ordinary human language. It exists only as an abstraction, a string of exponents, a reminder that we are still, for all our cleverness, working with matches next to a furnace the size of a world. Perhaps the more interesting question isn't whether we could ever destroy a planet with the tools we have now, but what it would even take, what forces in the universe, what stellar detonations or colliding neutron stars or ancient catastrophic collisions between infant worlds actually do operate on that scale. Because somewhere out there, they do happen. Planets do get shattered, swallowed, torn apart by forces far greater than anything in our arsenal. We just, thankfully, aren't the ones capable of doing it. Not yet. maybe not ever. And there's a strange kind of comfort in standing on a world that has already survived worse than our worst imagination, and will very likely go on quietly orbiting the sun long after we've stopped asking these questions at all.